In calculus, we often need to find the volume of complex three-dimensional shapes. These shapes are generated by taking a two-dimensional region and rotating it around a line. While rotating around the x or y-axis is common, today we will master the challenge of rotating regions around shifted vertical lines, such as x equals k. Understanding shifted axes is crucial for engineering and physics. Most real-world objects aren't perfectly centered on the origin. Learning to adjust our radius formula for any vertical line allows us to calculate the volume of almost any symmetric mechanical part or architectural structure using integration. Before we shift the axis, remember the standard disk method. When we rotate a region around the y-axis, the volume is the integral of the area of circular cross-sections. Each cross-section has an area of pi times the radius squared, where the radius is simply the x distance from the axis of rotation. If there is a gap between our region and the axis of rotation, we use the washer method. This involves subtracting the volume of the inner empty space from the volume of the outer solid. The resulting cross-section looks like a washer, with an area defined by pi times the outer radius squared minus the inner radius squared. Since we are rotating around a vertical line, we must integrate with respect to y. This means our function must be expressed as x equals g of y. Our limits of integration will be the lower and upper y bounds of the shaded region. Every slice is a horizontal disk with thickness dy. When using the washer method with a shifted axis, the outer radius r is the distance from the axis to the farther curve, and the inner radius r is the distance to the closer curve. Always measure these distances horizontally. The formula becomes pi times the integral of the quantity outer radius squared minus inner radius squared. To keep it simple, always subtract the smaller x coordinate from the larger x coordinate to ensure a positive radius. If the axis is x equals 5 and your curve is to the left, the radius is 5 minus x. If the axis is x equals negative 2 and your curve is to the right, the radius is x minus negative 2, or x plus 2. Our function is y equals the square root of x. Squaring both sides, we get x equals y squared. Our limits for y are clearly defined from the origin at y equals 0 up to the top boundary at y equals 2. Now we have our function and our interval ready for the setup. Wait, let's look closely. The region is bounded by the y-axis, x equals 0, and the curve, x equals y squared. The axis of rotation is x equals 4. The outer radius is the distance from x equals 4 to the y-axis, which is a constant 4. The inner radius is the distance from x equals 4 to the curve, which is 4 minus y squared. We set up the washer method integral. Volume equals pi times the integral from 0 to 2 of the outer radius squared, 4 squared, minus the inner radius squared, the quantity 4 minus y squared squared. Simplifying the integrand gives us 16 minus the expansion of the binomial, which simplifies further to 8y squared minus y to the 4th. Integrating 8y squared gives 8/3 y cubed, and integrating y to the 4th gives 1/5 y to the 5th. Evaluating from 0 to 2, we get 8/3 times 8 minus 1/5 times 32. This simplifies to 64/3 minus 32/5. Finding a common denominator, our final volume is 224 pi over 15 cubic units. What if the axis of rotation passes through the middle of the region? This creates a complex overlapping solid. In such cases, you must split the region into two parts and calculate the volumes separately, or rethink the geometry. Usually, in introductory calculus, we deal with axes that do not cross the region. Consider an axis to the left of the y-axis, like x equals negative 1. To find the radius, we still use right minus left. If our curve is x equals y, the distance is y minus negative 1, which becomes y plus 1. Don't be intimidated by negative coordinates, the geometry of distance always uses subtraction. Sometimes, converting a function to x equals g of y is difficult. If the algebra becomes too messy for the washer method, remember there is an alternative called the shell method. However, for many polynomials and simple radicals, the washer method with dy remains the most direct approach for vertical axes. Visualizing the result helps verify your work. The inner radius always corresponds to the empty space or hole in the solid. If your inner radius is 0, you have a solid disk. If it is non-zero, you have a washer. Always ensure your inner radius is smaller than your outer radius over the entire interval. Let's look at a symmetric case. Rotating the area between x equals y squared and x equals 2 minus y squared around x equals 3. The curves intersect where y squared equals 2 minus y squared, which is at y equals 1 and y equals -1. These will be our limits of integration. One of the most common mistakes is integrating with the wrong variable. For any vertical axis of rotation, whether it's the y-axis or x equals k, you must use dy. Using dx would describe a completely different rotation or require a different method entirely. Always check your differential before you start. Another frequent error is squaring the difference of the radii instead of the difference of the squares. Remember, it is r squared minus r squared. The area of a washer is the outer circle area minus the inner circle area. Mathematically, these are very different operations, and the first will lead to an incorrect volume. Finally, be careful with the order of subtraction. If you subtract the axis from the curve when the axis is actually to the right, you'll get a negative radius. While squaring it might hide the error, it can lead to confusion in more complex setups. Always think rightmost x minus leftmost x. To summarize, first, identify your region and the vertical axis x equals k. Second, ensure your functions are in terms of y. Third, determine your outer and inner radii by calculating the horizontal distance to the axis. Finally, set up and evaluate the integral from the lowest y value to the highest. The key takeaways are that shifted axes simply change the radius calculation. The geometry remains circular. By mastering the right minus left rule for horizontal distance, you can handle any vertical rotation axis with confidence. Practice sketching the region first to visualize the radii clearly. Here is a quick question to test your understanding. If we rotate the region bounded by x equals y, the y-axis, and y equals 2 around the line x equals 5, what is the expression for the inner radius? Think about which boundary is closer to the axis x equals 5. The answer is 5 minus y generated by Vision Solve AI.